Good evening, all. Let's get started. This 6 o'clock. We have more than 75% of participants here. Okay, so tonight, tonight's topic is basically Boolean algebra 2, that especially focusing on the digital design side, a part which probably not be a part of Math 42. If anyone wants to comment on that, like if you had Math 42 dealing with the K-map and everything, if someone can tell me.
Yeah, I didn't see the K map in Math 42.
Okay, so it mainly dealt with the identity formulas, those stuff, right, Carter?
Yeah, just the basic Boolean algebra operations and such.
Okay, so this is probably one new things that you guys need to pick up in terms of digital design to learn that part. So anyway, so I see a couple of questions there on the discussion side, but before going into that, let me take the poll for if you are prepared for this class or not. Let's take a minute to do that poll. Okay, I think all of you have participated in that. Let me end the poll, share the result with you. It's basically, if you see, there are 46 percent actually watched all of the videos, related videos, and 20% actually didn't see it. So I'm worried about them. Please catch up with the class. Uh, Similarly, for the lecture notes, those 17%, please do catch up. We'll deal about the questions. I hope you guys have more questions to me. But anyway, let's start sharing, start looking into those questions uh, about uh, about in the discussion. So we have someone from Carter. They're related. Explain the relationship between SOP POS, and this part we'll go through that. Then something about the grouping on the K map. It has to be rectangular. Charlotte, yes, it has to be rectangular. I'll probably explain it, but it has to be rectangular. Uh, like at least conceptually rectangular. Uh, can we walk through the consensus theorem and also drop non-essential prime implicant group? Yeah, we can do that too. Uh, okay, so let me see. Uh, so is there any other question? Or you can actually type in the chat, or I'd recommend it, if you have question, please put it on the discussion board so that we can refer to it in the future. So, all right, now the very first one, let's look at this example and this POS SOP relation and all this complement inverse, etc. Those discussion. This is mainly talking about those slides. I think you guys are looking for this one, relationship between SOP and POS. Let me try to explain that. So let's say I have a function. Okay, the function is expressed as a truth table like three variable x, y, z, and this one, right? Fx, y, z, and this is the output. And then these two columns is basically given for establishing the basically the fundamental definitions of the product term and what it looks like and what kind of what symbol we look write for those terms. And similarly for the POS, so this guy is related to SOP, sum of product, and this guy is related to POS, product of sum, where we define the sum term and the symbol for that. They are basically same. The only difference in the one is the capital and other is the small, capital versus small from symbol perspective. Now let's say I have this function, right? This function is let's say f x y z is your sum of term 0, mean term 0 to 5, 7. Now let's write down the complement function, right? How do we make a complement function in the truth table of the same function? So what we do, we replace 1 with 0 and 0 with 1 in the output column. So if it is 1 in the target in the function, non-complemented function, then in the complementary function it becomes like 0. And then if it was 0, then it will become 1. So according to that, my complement function to table would be 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. Okay. So my complement function, I can write it as this thing 1. So we are basically looking for mean term for this, which is 1, and mean term for these 2, which is 3, 4, and mean term for this, which is 6. So I can write 1, 3, 4, 6. Is that clear how I'm writing the complementary function in terms of SOP? Question so far on this? So this is purely by definition, right? This is purely by definition. So this means I have these this is like an M1 or M3 or M4 or M6. And now by the De Morgan, I can say that this is M1 bar, M3 bar, M4 bar, M6 bar, whole bar, right? This is by De Morgan. Now, now we have this observation is that the relation between any M0, like it's a sum term to the product term, is basically complementary. Like if you pick up anything, like for example, if you pick up let's say M4, right? Sum term and product term M4. Now look at this. M4 is X bar Y or Z, which is by De Morgan I can write X Y bar Z bar whole bar, which is nothing but M4 bar, right? So in general, we can say that any term Mn, the sum term Mn, is complement of corresponding product, right? Are we good? Any questions so far? Okay, so that means what I can write here is practically it is M1, M3, M4, M6 bar. That means my function, uncomplemented function, is going to be, so this is practically, I'm writing 1, 3, 4, 6 whole bar. That means this is nothing but M1, 3, 4, 6, right? So that's the relation between your function represented as a SOP, as a SOP versus the same function represented as POS. It is just a matter of like picking up corresponding terms, uh, sum terms or product terms from the truth table according to this rule that if we are writing POS, pick up the rows with zeros, and pick up corresponding um, let me just max term, okay, corresponding max term. So it will be I will pick up 1 max term 3, max term 4, and max term 6. Whereas if it is coming to the SOP writing, then I will pick up rows with a function value 1, and I'll pick up corresponding min terms to write my SOP. Okay. So this is what basically is being discussed in this slide, that it is been saying that if we are expressing something in a POS, there is a corresponding SOP, right? So that means they're like, they're nothing different. They're just an different expression forms, different writing forms of the same function. Either you are writing in a sum of product way or product of sum way. So that's why with that notion in mind, what we claim that further going forward in the KMAP discussion and others, we'll be dealing with the SOP only, because POS is nothing but an SOP. So there is equivalent SOP. Is that clear, Carter, Charlotte? You guys have this question. Or is there something else like bothering you guys on this part?
Yeah, it's clear for me. Thank you.
Okay, all right. Thank you. Oh, so you guys are messaging on the chat as well. Okay, I can see that. Well, the next one I wanted to is, let's say, prime implicant concept of that, right? And with that, I'll try to answer Charlotte's another question. Do we have to have a prime implicant groups as a rectangle? So, like mainly what we are looking for, let's say it's a 4 variable function we are talking about, let's say, mm, with ABC as a variable, A, B, C, D as a variable. So we are constructing the K-map. We are putting indices according to the gray code. And let's say this function is, let's pick a very simple function. ABCD is of sigma of, let's say, 0, 1, 4, 5. Now let's mark those boxes, indices box. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we look at this sum term, SOP, and place 1 with those boxes. So I'll just have 0, 1, 4, 5. Okay. So K-map reduction is all about, like visually look at the table and write down the reduced form directly without thinking of any identity formulas or anything. We just can write down the reduced form of this, and which is, in this case, we can write down it is A bar C bar, right? Because we see B is varying within this group row, so we are grouping. Let me mark the group. We are grouping these. Okay, and in that case, your within this group, within the row, B is varying, but A is constant at 0. That's why A bar came into picture. And within the columns, if you see these groups columns, your D is varying. This one column it is 0, other column it is 1, but C is at constant 0. So that's what the C bar came. So this actually gives you the directly form of the just hold on this. I have a sign problem. Okay. Sorry for that. There is a connectivity issue. Right. Okay, let's come back to this question. Okay. So what all we are trying to do is to reduce this form, and if we want to do it in the using the identities, right? Then what should we have done? So we should expand this whole SOP. We can expand that as a terms like M0 is A bar, B bar, C bar, D bar. M1 is A bar, B bar, C bar, D. And M4 would be A bar, B, C bar, D bar. And M5 would be A bar, B, C bar, D. Right? And then what we can do, so this, okay, first of all, these parts, so any term like this product term, we call it a product term or term with the and, they are called a they call these the implicants. So they are all implicants. They are all implicants. Now we pick up the implicants and then start using identities to reduce them. So to reduce it, what we can observe is that we can reduce them if they actually varied only in one variable form, like complement, non-complement. How, for example, if we see this group, that means group of 0 and 1, okay, this group, we can see they are varying only at D bar, D and D bar, right? So if we actually group them now, if we actually group them, these two together, then we can write it is A bar, B bar, C bar, D bar, or D. And similarly, if we group these guys, you see it's varying at D bar as well, right? D bar. Okay. So we can do this A bar, B, C bar, D bar, or D. Now you see this D bar, D is nothing but 1, right, by the identity. So what we can do, we can write it down as simply as A, B, C bar, and 1. And this guy would become A bar, B bar, C bar, 1, which is nothing but A bar, B bar, C bar, A bar, B bar, C bar, A bar, B, C bar. Okay. Now see, like now, even now, these are also called implicants. These are also implicants. Okay. Now we can now see that we have an opportunity to reduce around B. There's a B and B bar in place. So we can write this as A bar, C bar, B bar, or B, which is A bar, C bar, or 1, which is A bar, C bar. Now from here, I cannot reduce it further. Okay, so this is a product term. We still call it a implicant. This is still an implicant. But since it cannot be reduced further with combination of other things if they're present, right? We cannot reduce it further. It is called a prime implicant. And you see this prime implicant is directly derived out of the K-map visually, right? And for that, what we are simply doing is exploiting the neighborhood concept. Now, what is that concept? As we have used that, see in this case, it is these two terms are varying from each other only with respect to one variable, that is D. Both of them has A bar, both of them had B bar, both of them have C bar. Only D is varying. So we are calling them a neighbor. So in terms of the K-map, this is practically 0 and 1, which is we are talking about this group, 0 and 1. They are varying each other with D. See? And the other group, 4, 5, we have done this. They are varying with respect to D as well. And now, if we look at these groups, the other groups, like from the column wise, this group and this group, they are varying each other with respect to the B. Everything else is constant for them. So that's why we are actually combining them and expand them into a final group of 4 together. We are calling them, they are neighbor with each other. And we can actually go through all this reduction process actually. Theoretically, it is being done with that steps as defined in the K-map. So that's the concept of the prime implicant. That's the concept of the grouping. Now coming to the Charlotte question, since we are actually trying to group one way and also the other way, like side by side, it has to expand like a square or rectangle. We cannot simply do this thing. Let's say let's throw in another term. Okay, so here I cannot simply group this whole thing simply because that doesn't make sense in terms of this process what we described. It's practically combining two of them together. So that's why your groups has to be forming a number of like power of 2, either 2, 4, 8, those kind of groups. And since they have to be neighbor, these two condition actually dictates you that you will always have this group in a rectangular form. Make sense, Charlotte?
Yeah, that makes a lot of sense.
All right. Any other questions from anyone? Okay, now comes to the Carter's other question, is the consensus theorem. Can we walk through the consensus theorem, how it allows us to drop non-essential prime implicant group? Interesting question. Let's look at that. So let's say in the consensus theorem, what we are saying, we were saying that if, let's say is a function of 3 Boolean variable, and let's say xy, x bar z, and yz, all we are trying to say is that in this case, we can drop this term, right? So what this mean in terms of K-map? Let's think a little bit in deeper detail. So first, let's construct the K-map for us. So x, y, z, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Let's write down the indices 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now, let's talk about think like what would be the group in this K-map that would give rise x1? Means x at 1, so x at 1, and y at 1, y at 1, but z varying. Xy means x at 1, y at 1, z varying, right? So that means it must have been this and this, that groups. Oh, sorry, not that, this one, 1, 7, 6. So this is like sigma m 6, 7. That must be one prime implicant for me. And how about the next one? Next one is like, let's say this one, x bar z. That means x bar and z1 y values. So it must be this sigma m13. So this group gives you x bar z. Now, which group give you yz? Okay, which group give you yz? Yz means x varies, so x is varying, and yz is constant at 1. So that means it's practically this guy, this group, right? Now, in terms of K-map reduction steps, and so this is like M37. So according to K-map reductions policy, that these are all prime implicant. These are all prime implicant. PI, prime implicant. Prime implicant, prime implicant, prime implicant. But essential prime implicant, EPI, essential prime implicants are those which group has uniquely, like which are covering an unique one. So for example, this, if you look at this group of green, it is covering, no other group is covering this one, right? So that means my EPI is this one, and also this group is uniquely covering 6, this box, right? So that becomes my another API. But the other group that belongs to the YZ group, okay, this is nothing, it is not covering any unique one there. So we can actually, we don't need them in our process. So that's why we can drop it and my essential prime impedance list become 1 3 sigma and 6 7. Carter, is that make sense?
Yeah, that makes sense. Thank you.
All right. Any other question from anybody? Okay. Okay, enough of discussion. Let's take break. 5 minutes. 6:35. We'll be back. Okay, 5 minutes break. Okay, 6:35. Let's come back. Let's do a quick pop quiz. Please go to your Canvas page and see if you can find out the pop quiz number 5 and hit this poll yes if you are ready to enter the quiz password. Then I will relaunch another poll with the password on. Let's take a minute or so if you're ready. Okay, there are 29 of 35 of you are saying so 31 of 35, 4 more need to confirm. I'll wait for probably another 10 seconds to do so. 2 more, 35, 1 more. Anyway, let me launch the password poll. See if you can use it and hit yes if you can use it. Let's go to launch.
I have a question. Oh, he's gone.
Hey, seems like there is my original Zoom session has been hanged. Can you guys hear me?
Yes.
Yeah.
Yep.
Okay, let me see. Okay, sorry for that. Uh, yeah, I had to restart my system. Okay, all right. So I think most of you has done with the quiz, I believe. Let me check. Okay, where is my quiz board? Okay. Okay, so for this quiz, we have average score of 63% with 100% high. Um, and this is looks like your distribution of your quiz score tonight. Not bad, but we need to work on this average score, high score there. And I heard someone has some question during the quiz.
Professor, the quiz is muted. We cannot see the grade.
Oh yeah, okay, I will open that up. No issue for that. Just hold on. And okay, since I'm showing that one, I am done with your midterm evaluation. I'm just trying to give you the quiz statistics as of now. I will publish a score. I still need to go through some of the responses and also do some bookkeeping work before I publish the score. But your class statistics looks like this. Your average is 70%, which is just barely touching the pass mark, with a high of 96%. And your distribution looks like this. Like many people are in the 80% range, which is good. 80% and 90% ranges. But some peoples are there also falling behind these whole training. So that's what worrisome, and that's what basically brought down the average to 70%. So we'll see. Like I will try to publish it like within 2-3 days. And your average response time for this quiz is about 1 hour 11 minutes for every question. So that's not an worrisome issue there. I don't see. Yeah, so I wanted to share this before I shared your publish your individual score to you, so that you don't start panicking around. Okay, so this is your class distribution. Just make sure that you're going into these average category. If you are staying there or a little bit above, like 70% to 90% category, you should be good enough to go throughout the semester. If you fall behind the 70% score, that's where you need to put more steam onto your study process. Okay. So, okay, about that quiz. Yeah, I'll publish it. This pop quiz score, I'll publish it more.
I have a question.
Yes.
These pop quizzes are extra credit, right?
Yes.
Okay, cool. Thank you.
Okay. Okay, one thing I want to share with the previous discussion as we were doing about this neighborhood study. And so I want to tell that these mostly the groups are squared, as I say, but there are exceptions about the corners. Means, okay, let me actually use a different one here. Okay, let's take 4x4. 4x4 K-map table. And what is claimed? So it is grouping is all about neighborhood, right? So this is a neighborhood group. But in this process, your neighbor, these corners are neighbors too. So this corner and this corner are neighbor. And this corner, okay, let me put a different color. This corner and this corner are neighbor. Now this corner and this corner are neighbor. And this corner and this corner are neighbor. So overall, if you see a 1, 1, 1, 1 here in the 4 corner, you can actually make this 4 corner as a group. Okay, so that's the one exception where you don't see a rectangular grouping. It's kind of, I would say, conceptually rectangular because these corners are neighbor to each other, but it's not visually really a rectangle. Okay, that, let's do some one problem. Okay, let's say I have an SOP form like this. So we are given with this term SOP sigma of 5, 7, 12, 14, and with the don't care term 0 to 13, 15, what would be the minimized form of this equation, and also we need to write down all the prime implicants and essential prime implicant in the minimal SOP form, which is minimal SOP form means it's a sigma M form. Okay, just like I just shown you this form, like this is a prime implicant sigma M6. So it is practically telling you what groups I am making. Okay, so those are the prime implicant, and this is a minimal SOP form for the essential prime implicant identification as well. Let's make it a group like discussion, and I'll open up the breakout room for 10 minutes. You work in your group, discuss along with each other, and then we'll be back in 10 minutes and look at the final result. Okay. All right, I'm opening the rooms for all of you. Okay, I think all are coming back to this classroom. Anyone wants to share their result, at least the uh, final form, reduced form? No. Okay, so let me try to do it myself then to show you. Okay. So here in this problem, what we are trying to do is to deal with the don't care term. And as we all know, don't care. Okay, don't care means we can use those terms if needed for my reduction process. So we'll start with drawing the K-map for these things. So it's a 4 variable. So 4 by 4 K-map will be drawn. W, X, Y, Z. Put the indices. Let's round the index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, now from this SOP, this part, we place 1 at 5, 7, 12, 14. And then from this part of that SOP, which is don't care, 0, 2, 13, 15, we put X, 0, 2, 13, 15. Now what we do, we make a group. So essentially, if it was just 1, we don't consider X, then we probably would have make a group like these and another group like this. So we start with that. And now we ask ourselves, can we use any X as 1 that can increase my group size? We readily see, yes, if we treat this X as 1, then I can increase this group. So I refine my group, a bigger one. And similarly, using the same X, set of X, I can make a bigger group like this. We can increase this group of 12, 14 to include that one, 13, 15, and make a big group. So we'll do that. So basically, we increase the group. That means essentially my prime implicant, and in this case, it's the same as the essential prime implicant. I don't see any other choices. So it would become my sigma m 5, 7, 13, 15. That is one choice. And another prime implicant and essential prime implicants would be 12, 13, 14, 15. So essentially my function w, x, y, z will become wx for this group, because for this group everything else is varying, and for this group x is staying at 1 and z is staying at 1. So this become xz. So that's my reduced form actually. Okay, question? Okay, so as far as today's class is concerned, I think we have covered all the topics as we intended to do. There would be a quiz this Friday. I think Friday morning, 6 o'clock will open up, and I think you need to put it like submit it by 31st midnight, 11:59. That's number one. And what is the other thing? Oh, you have this programming assignment 8 due tonight. So make sure you turn in that as well. And the project, you can start playing with the initial source code and at least the first part, which is a normal ALU implementation, that you can do right away. Don't wait for the other discussion to happen. Okay, question? Okay, if there is no more question, then we can stop tonight and see you next week.